Okay, thanks for the nice introduction from Linjie, and I'm very happy to be here and share my recent research progress on the 3D reconstruction and the 3D generation. And today I will give a talk around the large reconstruction model and demonstrate how could we leverage it for the efficient and high quality 3D reconstruction and the 3D generation. So over the past year, we have witnessed the incredible progress of large language model. So from ChatGPT, it can handle very complex the human input language to the GitHub Copilot. It can also comprehend a very complex math symbols as well as the programming language like C++ and Python. And here I would like to show is performance on a very complex task. It's just to understand the human input language prompt. I just gave a very difficult instructions to ChatGPT. I require it to write a very short poem about the approach of using transformer to solve the image to 3D nerve translation. So this prompt is just the exact description for large reconstruction model. And here is the results. I think this task is pretty difficult for me because I'm not a poet. And but ChatGPT can generate this poem in a few seconds, like 3 or 5 seconds, and the results are seems pretty good. Yeah. So from two perspectives, the first perspective is it has a very good formats because in the poem it always has the consistent length, and the other thing is the rhythm essential property is also very good. So like the end word of each sentence, like the light, night, set, it always has a very good rhythm essential property. So here we have known that the large language model have demonstrated very good performance in various tasks. So what is the reason? What is the key to the success story of large language model? So the first one, I think it is definitely caused by a larger amount of the data. And the second one, I think it is the model itself. So let's give a very quick through to this plot. It is borrowed from the Hugging Face plot, Hugging Face blog that show the model size versus time series. So we can see in 2018, the best or the largest model at that time is Almo, but it only contains about 94 MB parameters. But just 4 years later, the best model changed to the Megatron Turing LG, and the model just scale up the 530 billion parameters. So I think this substantial increase in model size also emphasize that the critical role of the scaling up. So large language model has demonstrated the strong performance on various tasks. It is inspired me to ask a new question. So could we repeat the same story of large language model on nerve-like 3D problems? So before giving the answer, I think it is crucial to understand why we ask this problem. So I think all the peoples all live in the 3D world, and in addition to language, what we do all the time is to interact with the visual signal. And we will interact with the 3D objects, we will interact with the 3D scenes. So it is particularly important to understand the 3D world and then reconstruct 3D world for several vision-based tasks. And specifically, the current 3D reconstruction problem, reconstruction system have many problems. So here is a demo from Planvoxel, maybe the state-of-the-art algorithm in recent year for the 3D reconstruction, but it has many limitations. So firstly, they always need a very dense views. If you want to train a nerve-based method, you always collect the thousands of views to train a good novel synthesized nerve. And it also needs a pose estimation to get the accurate pose initialization. And then you can train this system to render photorealistic images. Because nerve is an optimization-based method, there's no data prior. It means if given a new novel scenes, you must rerun this optimization process again, and it always costs a long time. And most importantly, the nerve is a deterministic reconstruction system. There's no hallucination prior in this algorithm. So if you just given a sparse-view and there's no hallucination prior for the invisible part, it always make the reconstruction results very bad. So returning to our initial question, so can we just repeat the same success story to the 3D nerve-like problem? Our recent models have provided a positive answer. So this also helps to set the stage for today's outline. So firstly, I will introduce the large reconstruction model, and then I will introduce how could we leverage it for efficient and high-quality 3D generation for like the type 2 3D generation and image to 3D generation. And finally, I will give some introduction for my recent work called GRM. It has some fundamentally improvements, on the RM with the high rendering speed as well as the improved rendering quality. Okay, so let's start from LRM. So what are the goals of LRM? It just do a very simple task. Give a single image, I want to translate into the 3D nerve. So we always call this problem as the single image to 3D nerve reconstruction. But whether the single image or the reconstructed 3D nerve, it always characterizes the same semantics or the same physical object in the 3D world. So it means that it is just like similar to the language, we can transform this problem as a single image to a 3D nerve translation. We can regard the single image as the English language. And as well, we can also regard the 3D nerve as the Chinese language. And from this perspective, what we should do is not a reconstruction problem. It is just a language translation problem. Because in current stage, the language translation or the machine translation is a very easy solved task. We have transformer, we have birds, we have GPT-4. It has well studied in the language community. And it means that we have many well-developed techniques to solve this problem. So inspired by previous techniques, we just leverage the state-of-the-art architecture like the transformer to solve this problem. So because for the language translation, we always transform the input language in the token space. And what is the tokens for the input image? What is the token for the 3D nerve? Here we will give the answer. So for image, we have witnessed the VIT backbone like the Dino to give a very good representation learning algorithm in past few years. And we just use the VIT, the Dino pre-trained model to transform the input images into the token space. But how could we categorize the 3D nerve or the neural radiance field into the token space? We just use a trapline as an internal representation. So why we use a trapline? So trapline is proposed in EG3D and convolutional occupancy network. So it is very efficient because it just decomposes the neural radiance field in 3 independent plane. And it also very easy to generate with the neural network. It is compatible with many architecture like the convolution and the transformer. And the most important thing is that it is a hybrid representation. So the rendering will be very efficient than the original coordinate-based nerve. So here, we just randomly initialize some trapline tokens. And what we should do is just perform the 2D image tokens to the 3D trapline tokens translation. And it is a typically a language translation problem. And we just use a transformer as a backbone. And consists of several blocks, include the self-attention and cross-attention to perform association between trapline tokens and the 2D image tokens. And after use the transformer to perform the association, and we get the final output of the trapline tokens. And then we just use a reshape and spatial rearrangement for the trapline tokens to get the final trapline. With the trapline, we can train this this system with a multi-view image dataset. So at that time, we'll have the object-verse. It is a huge dataset, consists many 3D objects. We just use Blender to render multi-view image. And besides, we also include some real-world caption dataset like MV-EVNet. Because with the real-world caption dataset, we can improve the generalization and robustness for this system. The training is very simple. We just sample a single view image as the input, and then sample the remaining images as the null view image. We just use this trapline to render the images at the null viewpoint, use a reconstruction loss to train this system. Because it trains on a vast amount of data. During an inference, we don't need any test time optimization. We can directly put the image into this system and directly use it to inference the 3D nerve. Yeah. Here is the results on the full capture. So all the image. So I think the streaming is not very good, yeah, because for the reprojection. But okay, so here the 4 images are just taken by my own iPhone, and I just crop it at the center of this image and put it into the LLM. We can see the reconstruction image as well as the depths are very good. Besides, we also test it on the generative image, yeah, because in current stage we have witnessed many AI-based models like Stable Diffusion and Adobe Firefly to generate very high quality and photorealistic image. And we want to know whether it can achieve good performance on this synthetic image. And here are the results generated by the Firefly. I think even though it is out of domain image, because these images are not seen during the training, but it can also handle it very well. So even though LLM have many, impressive results, it can only use a single image as input and reconstruct the 3D nerve in less than 1 second. But it also has many limitations, because single view reconstruction is not typically a deterministic reconstruction system. It's somehow a generation problem, because you only have a partial observation. But what you want to reconstruct is or hallucinate is the unseen parts. So if we see this sample, we can see for the back view, it always has some black dot, and the textures are very blurry. It is just caused by the deterministic training of LLM. An easier way to handle this is we can convert it into the generative model. Like we can design some generative model with a similar architecture. It is the DMV3D. It is exactly what DMV3D do. And the other strategy is that we can leverage some multi-view diffusion model to firstly provide multi-view to provide or generate multi-view image with diffusion prior. Because with the dense view to characterize the 3D shape, the uncertainty will definitely decrease. And then we can build a multi-view or dense view reconstructor to get the 3D asset. It is a strategy proposed by Instant3D. Okay, so it is the first work of LLM. And anyone have questions about that? Okay.
For the tribe generation, with
sorry, can you repeat again? I don't hear clearly.
For the tribe, you have issues on cavity with the tribe.
Oh yeah, it is one of the limitations of that. Yeah. So because triplan cannot handle this case very well. So after that, we just inject some explicit prior like Gaussians to handle this. Yeah.
What do you mean by?
It is the final work I will present later. Yeah, and then we can discuss it. Yeah. Okay, so let's go ahead. So here I will introduce how could we leverage LLM for the efficient text to 3D generation. So I think in last year we have witnessed the Dream Fusion. It is a very popular text to 3D generation method. So we just use the diffusion 2D diffusion model as a prior and use the optimization-based methods to get the 3D assets. So I think it shares a similar problem with nerve because it is also an optimization-based method, and there's no data prior. It means that if you just give a new or novel prompt, it always needs a re-optimization process. And the other thing is the Dream Fusion is very inefficient. It always costs a single A100 GPU to optimize for 1 or 2 hours, and then you can get the 3D asset, and the quality is not as good. It's very good. But in fact, the diffusion model is already fast with some acceleration method like a DDM and the DPM solver. We can decrease the inference steps from 1,000 to 10 steps. So for example, if you just use SDXL or Adobe Firefly, it can always generate the image in 1 or 2 seconds. It is pretty fast. So what is the difference between the 2D diffusion inference and the diffusion optimization? I think it is just caused by the fast feed-forward network prediction. So the 2D diffusion just leverage the forward network prediction to improve the generation efficiency. So can we use this advantage to speed up the tag to 3D generation process? And we can just abandon the slow optimization process and instead use the diffusion model feed-forward prediction to achieve this task. So here is a comparison with our comparison between our methods and the SDS-based methods. We just leverage the feed-forward prediction of diffusion model, generate a multi-view image first, and then we just build a 3D reconstruction model to generate 3D asset very fast. Oh, sorry. Here is a pipeline for Instant3D. We just leverage the stable diffusion XL at the backbone model, and we fine-tune it to generate the consistent 2x2 image grid. And after that, we extend the single view LLM to multi-view setting, which can take the 2x2 image grid and output the reconstruct 3D nerve. So let's give more details for the first stage. How could we fine-tune a 2D diffusion model to generate consistent multi-view images? So I think the 2D diffusion models are foundational model. It is just like the large language model. They always, perform unsupervised pre-training on a huge data set, and then fine-tune with the human-aligned data to get the purpose the people want. And currently, what we want to generate a multi-view image. What we should do is just collect multi-view data to fine-tune it. And the strategy is very simple. We just render the observers in multi-view image, and then uniformly sample the camera pose and concat them into a large 2x2 image grid. We just use this type of data to fine-tune the 2D diffusion models. And here is the results generated by the fine-tuned model and the original model. We just feed the same prompt, and we can see, yeah, it keeps the knowledge of the 2D diffusion models, but also can generate a consistent multi-view image. Here is more example. We just sample some very complex prompt from the diffusion test set, and we can see it can also handle this prompt very well. The next step is about how could we efficiently convert the multi-view image into the 3D nerve. I think the only difference between this model and the LLM is just we switch the setting from single view to multi-view. We also use the same architecture, but the only difference is we will use the dyno to retry the multiple view feature from the input images. And we just concat it in the global token at the input. Then we just use the same strategy, the transformer backbone, to transform it into the triplet nerve, and use the same training strategy to get the final model. Okay, so here is a generated 2x2 image grid for the first stage diffusion model. And we just feed it to the transformer backbone, and we can see it can, reconstruct the 3D nerve very well and perform very high quality 3D asset generation. So with this system, we can make the tag to 3D from hours into minutes. And this system can generate high quality and diverse tag to 3D in 20 seconds. Here's a diverse generation results with the same prompt. It is more results generated by Instant3D. And if you are interested in our results, please check out our homepage. Yeah. Okay, so here I want to give some takeaway message from Instant3D. So Instant3D just decompose the 3D generation in 2 tasks. One is the multi-view image generation, and the other one is the multi-view reconstruction. So Instant3D just leverage the 2D diffusion model as a foundation model. It inherits a strong 2D generation prior. It is also one of the reasons why our model can handle very complex problems, because the diffusion model, like such as the stable diffusion XL, has trained on a vast amount of 2D text and image pairs, and it has a very good capability of understanding the complex problems. We just inherit this prior. But it also has some problem, because for the multi-view image generation, we only use the cross-attention mechanism to guarantee the multi-view consistency. There's no geometry constant. It always results in the inconsistent pattern at the local geometry. And with the inconsistent image, we always generate the 3D asset with the blurry texture and also have some artifacts. Yeah, it is a good question. So our multi-view generation is not a post-condition multi-view image generation. We just fix the input pose, so we just abandon it. Yeah, the poses are fixed for the training data. So I think it is a good strategy because it decreases the learning difficulty for fine-tuning the diffusion model. So in the follow-up work like the MV Dream 0123++, they always use the same strategy because yeah, it can improve the consistency after training this model. Yeah.
Doubts affected by the selection of your camera view?
Oh, it's a good question. So currently, our camera poses are sampled with the same elevation angle, and the azimuths are sampled uniformly around the circle. So if you just, yeah, I think this pose is a uniform distribution around this to characterize this 3D object. We also try to use some random pose, like as Yahoo said, maybe we can train a post-condition model, but the quality is not very good because the task is very difficult, more challenging than the uniform distribution. Yeah. Yeah, it is a triplan-based nerve.
So the way that you build a view is you actually do the ray marching sampling from like an NLP.
So we can back to the architecture. Okay, so what is the? Are you familiar with the triplan? Yeah. We just use the remarching to sample the features in the triplan, and then use the MLP to decode the color and density, and then yeah, it's exactly the same as triplan. Okay, let's go ahead. So we have known that even the Instant3D can have a very good efficient generation method for the Tattoo 3D, but it always suffers from the inconsistency of the multi-view image generation. So a straightforward idea is we can just merge the two-stage method into a single-stage diffusion model. But for the single-stage diffusion model, I think it has some problem. One is the 3D data distribution is very hard to learn. And the other thing is if we want to directly generate 3D asset, it always very challenging to add a random loss in the image space. And if that is the case, it always generate the image with the unrealistic texture. And here we just propose maybe we can learn to generate 3D, but not in 3D space. Also learn to generate 3D in the image space. And let's firstly revisit the LRM. So what LRM exactly do is, okay, we have a single view image and build a 3D reconstruction model, and then we just infer the 3D neural radiance field. We can also give the same pose to render the input image, right? If we regard the central part as a black box, it is typically an image-to-image network, like the pixel-to-pixel and the other image translation network. So in the diffusion model, we always know that the denoiser in diffusion process is also perform the image-to-image translation. But the only difference is diffusion model take the time as a condition, and it also take the noisy image as the input. And in this way, we can inherit the architecture of LRM because it can directly inject a 3D constraint in the diffusion process. So we just propose maybe we can use the LRM as a denoiser, but it has some problem because for single view to characterize the 3D shape, it has a large uncertainty, and you cannot, make sure that the back view always have all the invisible part always have a good results. So naturally, we just extend from the single view LRM to multi-view LRM, and it is a DMV3D strategy. We just leverage the multi-view LRM as the denoiser. So we just take a multi-view clean image, and then add a noise on the multi-view input. What we should do is just leverage this multi-view LRM to reconstruct the clean images. It is one step of the denoiser training in the diffusion model. So in diffusion model, we always need the text conditioning or image conditioning. So here, for the text conditioning, we just use the same strategy of stable diffusion. We use a clip encoder to get the text embedding and fuse it with the cross-addition into our LRM architecture. Now here is the text to 3D generation results. It only costs half a minute, and I think the quality is much better than Instant3D, but it can only handle very simple prompts. So why? Because as I mentioned before, the Instant3D can leverage the preaching of the stable diffusion. It is a wonderful reason that why Instant3D can handle the very complex prompts. But DMV3D just trained from scratch. We only have the object-verse data, and the object-verse distribution is not very well. So I just sampled some in-domain prompts and see what will happen. So if we just give a very complex prompt, the results are not very good. The generated objects doesn't align very well with a complex prompt. It is also one of the limitations of DMV3D. But for image condition, we have very good results. So here I will first introduce how could we inject the image conditioning. A straightforward idea is also we can leverage the image clip encoder to extract the embedding of the image and use the cross-attention to get to fill the image condition. But we found that it is very challenging to keep the identity of the input image because the clip embedding is very abstract. It cannot inherit any spatial detail of the input image. What we do is just propose a new view imprinting strategy. So in DMV3D, we have 4 views, right? And we just do a 4-view multi-view diffusion in the whole generation process. And what we do is that replacing the first view of the noisy image as the condition image for each step. And in this way, it is a very strong conditional signal to put the image condition and also keep a very good identity regarding the input image. And here is a diverse samples from the same input. Because DMV3D is a probabilistic model, we can sample different noise, and even with the same input image, it can also hallucinate different textures on the invisible part. And we also combine it with the SAM model to perform object scene level reconstruction. We first use the SAM to crop the object patches, and use the DMV3D to perform null view synthesis and the mesh reconstruction. Here it is the most popular demo of SAM. Yeah, we just use the we also test our model on this demo. We use the SAM to get the frog, and use the DMV3D to infer the null view as well as the geometry. Here are more results. Oh, okay, because what? Sorry. Okay. So after doing that, we have witnessed that the DMV3D can perform very well single view or image condition the 3D generation. So the next step is could we just inject these generated meshes into the traditional computer graphics engine? And in this way, it can help the graphic designer to simplify their, their content creation process. And what we should do is just fill this mesh into a Blender and perform some editing, like the translation, scale, as well as the rotation, to get compositional scenes. And here is the results of our rendering. So although it is not perfect, I think it is a good start, because I hope that this side of the generation model can reduce the difficulty of 3D design and also allow the average users to achieve the controllable 3D content creation. Okay, here I want to give some summary of Instant3D and DMV3D. It both to design for the 3D generation. So for Instant3D, it is a two-stage method. And DMV3D is a single-stage method. And Instant3D just inherit the strong prior in 2D different models, so it is better for tech to 3D generation. And the DMV3D just use a very, very strong conditional mechanism, so it is better for single view reconstruction. And the most important message from DMV3D is that we can use the 3D reconstructor as a multi-view denoiser. And in this way, we can always make sure the generated multi-view image from different model with the best consistency. And the other thing is that if you want to build a 3D generated model, it doesn't require any 3D ground truth. What we should use is a multi-view image and train a 3D different model. Okay, any question about the DMV3D?
Model, but all the prior-based nerves, none of them really use 3D model prior. They all use just a set of multiple views.
Oh, yes. So I think nerve is just like a underlying constraint. So it means what we really have access to is the multi-view image, right? We don't need any 3D explicit 3D representation. Like for previous triplet diffusion or mesh diffusion, you always feed the multi-view image into a 3D mesh or 3D voxel and perform the diffusion process. But in our model, we just use this nerve as an underlying constraint. But what we really generate is only the.
The ultimate goal is the novel right in the construction. That's the final goal.
Oh yeah, yeah. So from the perspective.
Just one method.
Yes, yes, yeah. It is a good question. For the. Yes, yes. So our ultimate goal, if it is only for the 3D asset, what we should do is perform the reconstruction for the 3D, like the 3D mesh, use some post-processing for the material methods. Yeah. Okay. So in previous 3 works, we always use the triplet nerve as the underlying 3D representation. But I found if I want to render a high resolution image, it always costs a long time. For example, it could take around 1.5 seconds to render an image from LLM. And if we want to generate the 2 seconds video consists of 60 frames, it always costs 1.5 minutes. And then in last year, we have witnessed that the emergence of 3D Gaussians. So they just use Gaussian primitives and a very fast rasterizer to get the real-time rendering for multiple images, and it can also achieve the much better quality than original nerve. And it inspired us that maybe we can use a Gaussian as the underlying 3D representation for the feed-forward model reconstruction. And here we just propose a very simple GRM. What we exactly do is we just replace the triplet tokens as the Gaussian tokens. Yeah, and we also use the single view to multi-view. Yeah, we use a patchify operation to get the 2D image tokens firstly, and then we just use a transformer to transform the 2D image tokens into the Gaussian tokens. And different from the original Gaussian, we don't predict the XYZ location. Instead, we just predict the depths, because here we just use a pixel line Gaussian, because pixel line Gaussians always have a less freedom for the points distribution. And in this way, it can make the training more stable and the results are much better.
How do you then take so for one view, a specific depth, but you still take this Gaussian and render it in the other view?
Yes, yeah. It train. Because I have just used many details for the previous works. I think that these models share the same training strategy. It always, use the null view as a supervision and use the reconstruction laws to perform training on these models. Yeah. So in conventional patch file operation, it always downsample the image in a low resolution feature. It means that the pixel line Gaussians generated by the transformer also have a very limited resolution. To improve the spatial modeling capacity, we always introduce a transformer-based upsampler to scale the low resolution image token to the high resolution, Gaussian tokens with the same resolution of the input images. And after that, we will fuse these multi-view Gaussians into a global point cloud, and then we just sample the null view camera viewpoints and render to get the null view images. With the multi-view ImageNet and Object-Verse, we can train this model very well. And here is the sparse-view reconstruction. Because it is a feed-forward model, and the Gaussian can perform real-time rendering, only taking 4 images, the GRM can reconstruct the null view image depths from cloud as well as the mesh. Very, very good. Very good very good high quality. I think it just hallucinate new Gaussians. Yeah. Here are more results. So because GRM is a general feed-forward reconstruction model, so it is compatible with many models for 3D generation. So for example, we can use some text to multi-view generator like Instant3D, the first step of Instant3D, and also some image to 3D model like 0, 1, 2, 3 plus. And we can also integrate GRM with many video generation model. So like SV3D from Stability AI and V3D from Tsinghua University. They just give a single image prompt at the condition, and then they can generate a consistent video for the input image. So here it is a different output format for this model, multi-view image as well as the video. What we should do is just use GRM. What we should do is just sample 4 images from the output of these models and just use the GRM to perform very fast 3D reconstruction. And here is the rendering Gaussians as well as depths of the results. So here are more visual results for Instant3D. And it is a 0, 1, 2, 3 plus version 1.1 with the GRM. So for SV3D, it always generates 21 frames video for the input image. And we just uniform sample the 4 frame from this video and then use the GRM to reconstruct it. So here is a Blender scene with our 3D assets. All the 3D assets are generated or reconstructed by GRM. So okay, any question about GRM? Oh, it is a good question. So I think it is caused by the insufficient input view, also the insufficient training. So the first perspective is we just input the sparse views, and I think for some very complex objects, the sparse views cannot cover all appearance details. It is very hard, right? And the second thing is that I think our released model are not trained very well because we have limited GPU resources. So if we can further scale up the model and the model and the data, I think the reconstruction results will be improved. Yeah.
How long?
We just trained it for 4 days. Yeah. 32. But in DMV3D, I think the results are pretty good because we just trained with 100 GPUs for 10 days. Yeah, it is a large gap between the computational resources. Yeah, we have visualized that. So I think with the sparse Gaussians to represent scenes, it always have some low fidelity texture. Yeah, particularly on some sharp details. Yeah, it is a wonderful reason that why we propose the upsampler to hallucinate the new Gaussians and then facilitate the better reconstruction. Oh, so in that case, we don't have ways of the Gaussians because we will perform the mask at the input image and filter all the background points. It is a first perspective. And the other thing is that it is a good point that maybe we should use some deformation or learn some offset along the rays because in this way the Gaussians will have better representation capacity because particularly on some invisible part, right? So I think for the sparse view setting, it cannot cover all the details. But if you just use some deformation field along the rays, it somehow can hallucinate more details around the invisible part. Yeah. Mm-hmm. Yeah, but because we have the ground truth mask, and we also have the alpha regularization during the training. So it means we know which pixel is the foreground and which pixel is the background. And we can filter these points in the rendering. Yeah. Yes, yeah, it has some ways of computation, but it doesn't have any effects on rendering. Yeah. So maybe we can also do some mask transformer during the feed-forward prediction process. We can have the ground truth mask, and we can set this set this background points as evaluate like some class token and with the specific token. And in this way, we can just improve the training efficiency. It's also a good strategy to improve that. Yeah. Yeah, a good strategy is we can perform a small dilation. Yes, do some dilation and include several points. I think it only increase only a slightly increasement on the computing cost, but don't affect any performance, right? Mm-hmm. Yeah. Yeah. Honestly, we don't need that much. But the reason why we use that is we think the more Gaussians always results better results. And we also design some engineering tricks to make the small GPU can handle many Gaussians. So we don't remove that. But if you just want to model, I think maybe if you want to improve the efficiency, maybe a good strategy is just filter out some invalid points. Yeah, like the mask filtering, as well as some density pruning. If for some Gaussians with a low opacity, you can directly prune it for the rendering process.
Right. Better like using more Gaussians and then components or Gaussians instead of using that.
We don't do a very comprehensive study, but maybe I think it had a comparable performance, maybe. Yeah. Okay. So, finally, I would like to give summary for today's talk. So I think in terms of literature, the research always distinguish between the 3D reconstruction and the 3D generation. So for the 3D generation, we always make the model to learn the probabilistic distribution, so like GANs and the diffusion models. We always sample different noise and want the different model to generate diverse output. But for the reconstruction, we always collect many views to train a reconstruction model. So this system can be very deterministic. So how could we bridge the gap between these two tasks? I think the single view or sparse view conditioned 3D generation is just the key to bridge this gap. So for example, like DMV3D shows, the single view input can also generate a diverse output with the invisible part. And if we just increase the view from 4 to 6, maybe to 10 to 20, and the shape uncertainty just decrease, and it just make the 3D generation to be a 3D reconstruction problem. So I think the most important issue in the 3D is also the 3D representation, because the 3D representation is the link between reconstruction and rendering. And when there is a stronger reconstruction system, the 3D generation will also be better. For example, currently we have GRM. If we want to use GRM to do a Instant3D like work or DMV3D like work, it always have the better generation quality and the generation efficiency. And here, I just want to use a one sentence to summarize today's talk. It is the better we reconstruct and the better we generate. And I hope in the near future we can witness many 3D fundamental emerge and further improve the current 3D research. Okay, thank you. Thank you for listening.
Yeah, thank you, Yinghao, for the amazing talk. Any questions from audience?
Thank you so much. So like for context for my question, I'm working at a startup where we're applying a lot of 3D reconstruction techniques in the robotics context. So as a robot is like moving around trying to reconstruct the environment, and in the robotics context, for each image, you may have different kinds of uncertainties and information. Like you may have a good depth map or some prior like reconstruction, but some other parts of the image are not fully reconstructed. And I'm curious, in the future, do you see these types of models transforming where you don't just give an RBG image, but maybe you give the partial like reconstruction with your uncertainty, with the depth map, with the surface normal map, and kind of all the other information you may have about what you think that is, and let that model incorporate that to generate the final.
So I think it is a very good question. So your question is, I will say the question first. So your question is, could we just extend this system to some robotics related input like some depth map and RGB with partial observation and with some uncertainty, right? Yeah. So I think it is a very challenging task, because if you want to recover the whole 3D shape from the partial input, it is not a reconstruction model. It's also a generative task, right? So to solve this problem, I think we can handle two types of setting. The first one is, how could we handle the input with that larger uncertainty, right? Currently, we just use the deterministic RGB camera to handle the pixels. So I think if we want to handle the uncertainty input, what we should do is just put away leverage some prior to decrease the uncertainty or compress it into a very compact latent space. I think it's just like a RGB camera. It always take some when it just perform the imaging, it always handle some uncertainty, but it always output the deterministic output, right? So from this perspective, we just need a compression model, just similar to the imaging device, just transform the uncertainty input to a deterministic input. And in this way, we can just use our system. And the partial observation using partial observation to reconstruct the 3D scene. I think we need many generation prior from like the GAN or diffusion models, because only use the partial observation to generate the invisible to reconstruct invisible part is impossible from my perspective. Yeah, the 2D diffusion model or video generation models can always generate the very good or realistic video sequence from the partial observation. And in this way, we can just leverage it to impend it at the image space, and then use this model to perform large-scale reconstruction.
Thank you for your talk. So it seems like most of your earlier work, you were trying to regress these triplanes and then doing triplane nerves. And then their most recent work, you were spitting out these Gaussian clouds.
Yeah.
Do you think in 5 years, Gaussian clouds are what we're still going to be using? Is this like the right representation to represent 3D? Or do you think that there's some evolution still left for like having a flexible but compact representation for 3D?
Oh, it is a very fundamental question. So from my perspective, I think in no-view synthesizer, I think Gaussian will dominate the next few years, because it's very good representation power as well as the render speed. Yeah. So even though mesh is good, it has a very fast rasterizer, but it cannot handle the background or large-scale scene very well. But if you pay more attention to the simulation or pay more attention to physics, I think the mesh will also dominate this field, because we just develop many mutual algorithms to detect the collision, right? To model the dynamics of physics. Yeah. So it is just depending on what you want to use and what is the task you have used for. Yeah.
Do you think there will be some representation that unions the two, or has some like, great, in text, we've managed to find that tokens can just do all the text tasks that we care about?
Yeah. So currently, I saw many reconstruction systems always leverage the combination of mesh and Gaussians, because they always want. I don't know what is the future, but currently I think they just use mesh and Gaussians for different tasks. Yeah, what they do is just regularize the Gaussians during the reconstruction, and then they can have a good isosurface from these Gaussians. Yeah, maybe from my perspective, I think Gaussian is not perfect. What we should do is do some or develop some virtual tools for physics and all the simulation. And in this way, if we can find a very good or mature algorithm to solve this problem, I think Gaussian will solve everything. It is just my perspective. Yeah.
Thank you.
Any other questions from audience? The last question due to limited time. Okay, if no, then I have a question. So I think most of your work focused on object level reconstruction. How do you see how far to the scene level reconstruction, and what is the challenge there to extend your current approaches to scene level reconstruction and generation?
Oh, so yeah, because I also witnessed the limitation of this works, and currently I'm just developing a new system to handle the scene reconstruction. But I think the most challenging thing for scene is also the representation, because if you want to render a very large scale scene, not the local observation of the large scene, it is just like a CETO level scene. I think how could we find the efficiency 3D representation is very difficult. Yeah, but our current setting is also paying more attention to the feed forward scene, like some scenes with less camera motion. Yeah. So and in the industry, I think Gaussian is enough to handle it. Or some composition with traveling can also handle it. Yeah. So as I mentioned, I think for the future research in 3D, not only on the scene but also on the object, the most critical problem is also the 3D representation. Yeah. If we can find a large scale, compact, and efficient 3D representation, I think this problem will be easily to solve. Yeah.
Thank you. Thank you everyone for attending this talk. Yinghao.